Welcome to this explainer. Today, we're deploying straight into the high-stakes, highly tactical grid of mobile ad hoc networks to uncover the hidden mechanics of the OLSR protocol. Let's get right into it.
So imagine being dropped directly into a totally chaotic battlefield of nodes. Communication is absolutely critical, right? But the network's topology? It's entirely unpredictable. You've got devices moving around, signals dropping left and right, and yet, you still need to guarantee that your data gets exactly where it needs to go, instantly. So how exactly do you pull that off?
This brings us to Section 1, the challenge of MANETs.
You see, a MANET, or Mobile Ad Hoc Network, has absolutely zero permanent infrastructure. We're talking no fixed cell towers, no underground fiber optic cables to rely on. Literally every single node, whether that's a moving vehicle, a drone overhead, or just a handheld device, is completely on its own in this highly dynamic wireless theater. Standard routing protocols, the ones built for wired networks, they just fall apart here because messages are incredibly prone to loss or collision as that topology constantly shifts around them.
To handle all this chaos, we basically have two strategic options. On one hand, we've got reactive routing. These protocols act on demand. They only discover and establish routes when a node actually needs to send data. But on the other hand, we have proactive routing. And this is where it gets really interesting. Proactive routing means the nodes are continuously exchanging control messages. They are maintaining up-to-date routing info for all nodes, regardless of whether a route is currently needed. They're basically always mapping the battlefield to guarantee instant data delivery with absolutely no route discovery delay.
Which leads us to Section 2, proactive routing with OLSR.
Enter OLSRv2, or the Optimized Link State Routing Protocol. As detailed in the IETF RFC 7181 standard, OLSRv2 is this proactive, table-driven protocol. It continuously exchanges topology control, or TC messages, so that routes are immediately available. And what's cool is it doesn't just lazily look for the fewest hops, it actually utilizes additive directional link metrics to calculate the absolute highest quality, shortest distance routes. Because those metrics are directional, the protocol understands that, hey, the signal quality from node A to node B might actually be entirely different than the signal coming back from B to A.
But maintaining this constant stream of telemetry creates a massive vulnerability. Section 3, surviving the broadcast storm.
To maintain those proactive routing tables, nodes obviously need to constantly broadcast their status. But think about it. If every single node in a dense network just blindly floods every control message it receives to all of its neighbors, and then those neighbors forward it to all of their neighbors, well, the network quickly collapses under its own weight. This is a very well-known vulnerability called the broadcast storm problem. The network just becomes completely paralyzed by excessive broadcasting. So the big question is, how do we stop it while still keeping the network perfectly updated?
To stop it, we use the absolute hero of this explainer. Section 4, multi-point relays, or MPRs. Instead of having every single node shouting over each other all at once, OLSR uses multi-point relays. Think of these MPRs as your designated signalman in a tactical command chain. Basically, a node selects a specific targeted subset of its immediate neighbors and designates them as its MPRs. When a node sends out a control message, sure, all of its neighbors hear it, but only those pre-selected MPRs are actually authorized to broadcast and forward that message further out into the network. This incredibly simple rule dramatically reduces the number of transmitter nodes and slashes overhead.
Now, the crucial part here is understanding the rules of engagement for how a node actually picks these MPRs. First, we identify our one-hop neighbors. These are your direct, immediate neighbors that you have symmetric, bidirectional links with. Then we look at our two-hop neighbors, so the neighbors of your neighbors. Your ultimate tactical objective here is to select the absolute minimum number of one-hop neighbors as MPRs, while still ensuring that a full 100% of those two-hop neighbors can receive the signal. You really have to choose the perfect subset to guarantee your data hits that outer perimeter.
And this brilliantly illustrates the depth of the protocol. RFC 7181 actually separates these MPRs into two distinct roles. First up, we have flooding MPRs. These are designed specifically for flooding reduction using outgoing link metrics. They're the ones managing that crazy broadcast storm for control traffic. Second, we have routing MPRs, which are designed for topology reduction. They use incoming neighbor metrics and take on the heavy responsibility of acting as intermediate routers, advertising link states to calculate those shortest, metric-based multi-hop paths. And a node can actually be one, both, or neither of these at any given time.
But here is where the network's self-awareness really kicks into high gear. Not all nodes are created equal, right? Some devices might be running on a dying battery, while others could be plugged straight into a permanent power installation. To account for this, the RFC defines a brilliant concept called willingness. Nodes constantly advertise their willingness to shoulder the burden of being a flooding or routing MPR. If a node is dying, it can just advertise a willingness of will_never, which is a numeric value of 0. It's essentially telling its neighbors, look, do not pick me to route your traffic.
Conversely, a node advertising a willingness of 15, which translates in the protocol to will always, literally commands the network to always select it as an MPR. By doing this, the network autonomously takes the heavy lifting off those weaker nodes and intelligently routes the complex traffic right through the nodes that actually have the resources to handle it.
Section 5. Executing the NPR selection. Let's zoom in and look at the tactical execution of how this is actually done. This selection algorithm basically happens in 3 stages. Step 1. The node looks at all of its 2-hop neighbors and finds the isolated ones, the targets that can literally only be reached through one specific 1-hop neighbor. It immediately locks in those 1-hop neighbors as MPRs. I mean, you have to secure the isolated targets first, right? Once that's done, in Step 2, it evaluates any 2-hop neighbors that still aren't covered by that first group. Finally, in Step 3, it optimizes everything else by picking the remaining 1-hop signalmen that have the absolute widest reach, maximizing coverage while keeping the total number of MPRs as low as possible.
To really see this in action, imagine you are node U, sitting right in the center of a NetSim 3D grid simulation. You're operating in a 1,000 meter by 500 meter space, constantly parsing live telemetry through regular hello messages. You can clearly see your immediate 1-hop neighbors like nodes B, C, D, E, F, G, H, and I. And you can also see those 2-hop neighbors sitting just beyond them. Now you have to figure out exactly who your MPRs need to be to establish full 100% connectivity without flooding the zone.
Looking at this live telemetry log flowing from NetSim, we see node U's logic play out perfectly. It dynamically selects node E first. Why? Well, because node E provides simultaneous coverage to multiple 2-hop targets, specifically nodes P and N, giving it the highest degree of connectivity on the board. Then, to reach node L, it selects node C. It just continues to iterate on this logic, dynamically adapting until the MPR set fully stabilizes at nodes C, I, G, H, and E.
By prioritizing nodes with the highest degree of connectivity and actively adapting to their advertised willingness to serve, the MANET completely transforms. What could have easily been a chaotic, system-crashing broadcast storm is completely mitigated. Topology reduction is finished, and those optimal, metric-driven routes are fully established. The network has essentially organized itself into a highly optimized, stabilized communications grid with absolutely zero centralized control.
Which leaves us with a pretty wild final thought to ponder. As these tactical networks scale up into massive swarms of autonomous vehicles, low Earth orbit satellites, and billions of connected devices, could this exact, decentralized, self-healing mechanism become the blueprint for how all future global infrastructure communicates? If a network can organize itself this well in a chaotic battlefield, perhaps it holds the key to a truly indestructible planetary internet. Thank you so much for joining me for this explainer, and keep questioning how the world connects.